Okay, hello, I'm Dr. Momita Das, and I'm from the Hong Kong University of Science and Technology. So today I will be presenting my paper. The title is a blockchain-based encryption method for IFC models for collaborative project management. The introduction slide, it shows you the construction data in collaborative project management. So there's different types of data like documentation, fabrication data, etc. But in the heart of all this sits building information modeling. So basically the integrated BIM model, and it contains a lot of sensitive information because of which the security of the BIM model becomes one of the prominent things to consider. Now, the importance of security of BIM information sharing has been highlighted by the ISO standard 196505, and it recommends that built asset security management plan be created to protect confidential information in BIM models. So it recommends considering various security related aspects. So a few of them, for example, the first one is confidentiality, basically protecting sensitive information from being exposed. Then integrity, which basically means that making sure that the data that you're accessing is has not been modified by any unauthorized users. And then this standard also recommends that like where you do implement methods for protecting confidentiality, integrity, etc. But at the same time, you need to make sure that the basic functionality of the BIM model, the data, is not severely hampered. So we will look at the requirements of BIM security in the following slide. So the basic property of BIM models in a collaborative project environment is that there are multiple data owners. So in this case, in this BIM model, there are just an example. So there may be several systems, but each of the system data may belong to a different owner. So which basically means that there might be different data owners. So it becomes necessary to protect the sensitive information so that only the right user can access them. And here are some examples of sensitive information in IFC files. Information such as material information, occupancy can be sensitive. Design of IFC elements, the design itself can be an intellectual property, so the data owner might want to protect that. Other than that, cost related information is also can require security measures. Now, just an example application of data confidentiality for design management. So in design management, there might be multiple parties involved like owner, architect, structural engineer, etc. So what our method does, it encrypts different parts of the BIM model in such a manner that only the data owner or the rightful data user is able to access it. So by doing so, what we do is we provide a method to have multiple views on the same BIM model. So for example, architect will view his model, the structural engineer can view his own model without accessing the architect's information. So this is particularly applicable where you have a federated BIM model in a common server and there are a lot of parties who are accessing that. Now, the proposed method of data confidentiality, the reason why it's an improvement over existing methods of encryption is that if you use existing standard methods of encryption such as AES, so AES of course is robust in itself, and our approach is not about improving in terms of improving over the robustness of AES, but it's about the accessibility of data. So, for example, the existing encryption methods, what you can do is you can encrypt a whole file. So if you have documents or a BIM model in file format, so you can encrypt it. So in that way, what will happen is you can give an user a complete access to that particular document or file, or you can completely revoke end user from accessing that Beam model at all. But in our case, using the proposed encryption method, what we do is we encrypt different parts of Beam model using different encryption keys, and we leave some of the non-sensitive data in the Beam model as unencrypted. So what you can do is, using this method, you can give access to different parts of the Beam models to different users through encryption, so which is not possible using standard methods of encryption. Now, moving to the system architecture of the proposed method, so it mainly has four layers. The first layer is data segregation encryption layer. The main purpose of this particular layer is to extract sensitive information out of Beam models and then put them into different encrypted files, and then encrypting them based on the data ownership. And the other important function of this layer is to also to make sure that these files can be decrypted and then be put back into the original IFC file, so that the data owner can access his own part of the Beam model. Now, the second layer is the encrypted data indexing layer. So the main purpose of this layer is to store the encrypted files and also provide a method to search over these encrypted files without having to decrypt it, using some predetermined keywords, popular keywords. These keywords can be material name, building element name, zone name, etc. Now, the third layer is the blockchain layer. So the main function of this layer is to provide data integrity. So whenever an encrypted file is uploaded to the common server, or non-encrypted file is uploaded to the common server, so a record is created in the blockchain and a hash record is also stored in the blockchain. So this is particularly to ensure that whenever later an end user downloads the encrypted file, so he can make sure that he can be sure that the file hasn't been changed from the time that it was uploaded by verifying with the hash records present in the blockchain. And the final layer is the access control layer. So it basically, I will not go into the details of it, so the details are present in the paper. So what it does is it allows customizing of encryption keys. So suppose this encryption key was used by the data owner to encrypt the files, the green key. So he can send it to an access control manager, and by using proxy re-encryption, so the access control manager gives it to the different end users without decrypting the original key, so the secrecy is maintained. Then the functionalities of the data segregation and encryption layer, two main functions. One is full encryption, another one is partial encryption. In full encryption, what we do is we the sensitive elements. So if this particular exhaust system is sensitive, so what we do is we take that out from the Beam model. So like you can see it here, and then we encrypt this part separately. So in that case, you will have this base model which contains non-sensitive information which can be shared with everyone. And after decryption, the file on the right hand side, this picture, so after decryption, those encrypted elements can be put back into the IFC file and the whole model can be viewed. Now, the second one is partial encryption of IFC files, which is rather more useful. So it hides the sensitive elements, but it retains functionality such as clash detection, and also retains the aesthetics of the model, because what we do is, in this case, like you can see encircled, the original building model has a supply unit. The design may be a little complex. So what we do is we simplify the geometry of it, and if necessary, we remove the properties, etc., if it is sensitive, and then we put it back to the encrypted Beam model. So we have the elements, all the elements in the encrypted file, but at the same time, it is the details are not present. The methodology for partial encryption of IFC files, we use this method. So we use IFC faceted BREP. So this is a BREP representation which takes the vertices of a building element and then puts them into IFC Cartesian point. It has its own format to represent a building element. So using this, what we do is, suppose here in the slide, you can see this encircled rainwater faucet. So suppose this is a sensitive element and the data owner wants to hide the geometric details of it. So what the method does is it extracts the geometry of this particular element, and the representation can be in any IFC format like swept, solid, brep, etc. And then it converts the geometry into a mesh format, which is basically vertices and faces. And in order to simplify the details of this particular element, what we do is we get only the outermost vertices of the mesh, and we perform a convex hull. So, and then we put the vertices of the convex hull, the model, into IFC faceted brep, and in this manner we create a simplified IFC element. Now, some of the examples of the element that we have simplified is here. Finally, this example scenario showing the application of this layer. So there are two main data owners. Architect, the model is not sensitive. He uploads it to the common data environment directly. The MEP engineer, however, his model is sensitive. He has two systems. So what he wants to do is he wants to hide the details of these two systems, and also wants to ensure that system 1 is accessible to subcontractor 1 and system 2 is accessible to subcontractor 2. So using our method, he encrypts these two systems partially with two different keys, and then he uploads them into the common data environment and blockchains them at the same time. So in the common data environment, users can perform functions such as clash detection using the architectural model and the encrypted IFC model, MEP model, and perform issue management like create issues, and if the architect is the responsible party, send it to him and can solve the issue, or if not, the architect can write back that there are problems in the issue. And at the same time, the MEP subcontractor 1 and 2, they can download their own encrypted, their accessible encrypted files, and they can put it back into the base MEP model and can view their parts only. Now, for implementation, we have used Python encryption libraries and IFC OpenShell for the IFC parsing, and we have used Hyperledger for the blockchain part. For implementation, and here in this picture you can see there's an encrypted model, there's a decrypted model. In the encrypted model, for example, this wall that is shown by the arrow, the generic structure of the wall is retained but the details are hidden, but in the decrypted file the details can be shown. The initial results of evaluation, so we have considered we have considered architectural model, and shows that the entities of the IFC file is not lost in the original and the decrypted IFC file. Now, finally, the blockchain results. So we have tested latency and throughput of on Hyperledger Fabric, and the results are within the permissible limits. And finally, to summarize, we have presented a method to segregate and encrypt sensitive information, and also to perform searching over encrypted IFC files. And in future, we will use complex IFC models from an ongoing Hong Kong-based project of Kaita's Spark to validate the methodology. So that's it from my side. So thank you very much for listening. So unfortunately, I couldn't present this in person, but this is my email ID. So if you have any questions, you please feel free to reach me. Thank you. Thank you for listening.